All right, can you see it now? Okay,
Yes, we
sorry
can.
about that. Okay, good. So let's come back. I was just presenting this slide, and I was speaking about the left-hand picture in which the region is shown for which the model is created. So this is the area in Mexico that is relevant to us, and from which we have gotten this business need. And then in the middle picture, you can see some increased image of the area with some wind speed. And then also here are some vertical cuts which are performed from north to south. And then you can see these cuts at the right-hand side of this slide. And if we present all the wind speeds, so the colors, as I've said, are corresponding to the wind speeds in this cross-section. And there are certain critical weather events that are visible and that are sometimes happening. One is called hydraulic jump, and the other one is called downslope windstorm. And some expert in the field, which is not me, which is actually my colleague Miguel, can directly by visually inspecting these images detect which of these phenomena is currently visible. And this is what we are going to predict, or these are the two critical phenomena that we want to detect in the end. So yeah, then you can also see at the bottom of these images the orography, so the mountains, and where the wind speeds are passing the mountain and how these patterns are evolving then. All right. Let's speak a bit more about these extreme wind events. Actually, there are two critical wind events that we are going to predict with the model. As I've said, the downslope windstorm and the hydraulic jump. But then, of course, it's not always the case that we have these critical patterns. So, of course, we also want to predict and differentiate the critical events from the normal events. And that is what you can see here at the right-hand side at the bottom picture. So this is some example of a normal situation. And also what you can see here is the dimension of the domain that is used. So here you can see that we are simulating and extracting from our simulations a height of 4 kilometers, and the horizontal distance is 100 kilometers. Okay, and also once we are able to detect these patterns, of course we want to make the best use of it, and we are using it in a way that we are detecting these specific critical events, and then we are sending alerts to the stakeholders, and the stakeholders could be site managers, so they can then take the proper actions to protect the people in the area, possibly service workers, but also the assets in the wind farm, because these wind events could actually create some harm to the turbines. Now we want to speak about this, what we call extreme wind events forecasting system. And this system is based on a pipeline, which is having several steps. The first step is WRF. So the WRF system, which is our operational weather forecasting system, is making use of these numerical weather prediction models, and we are creating simulations for the region of interest. And from these simulations, we are extracting images. Like I've said, you can see it also in the middle here. We are extracting, with the help of these vertical cross sections, images, and then we are taking one specific quantity, the wind speed, and use that for coloring these images. And then we get the cross section and can see visually the distribution of the wind speeds in this area. And then we are simulating a longer time period, and we are having for the complete time period with a resolution of 10 minutes the predictions of these areas. And then this is just the starting point. So this is just the WRF system. and the output of the WRF system, the images, are then fed to the deep learning model, which we have trained to detect these critical weather patterns. Here you can see the algorithm and a high-level representation of the model development. So we are starting with the WRF simulations of the region, and then we take these images, and that was the majority of the work that my colleague has performed. All of these images had to be manually labeled so that we have a good training data set. So we have then a large bunch of different images which are putting into different boxes. One box is normal wind behavior, then we have hydraulic jump, and then we have downslope windstorm. And in total, you can see the dimensions here. We have classified more than 6,000 different images, and these are having the dimensions horizontally 80 pixels, vertical 102 pixels, and then there is just one color channel. This color channel is representing the wind speed. So we are just using one color channel, because we don't need colored images. Some grayscale images, like we have seen on the slide before, are totally enough for the purpose of what we want to reach here. And it's reducing the numerical effort if we just use this one dimension here for the colors. So basically, we're working with this four-dimensional tensor. And if I say images, we actually did not extract images as image files, but these images are just encoded as arrays in the end. And then we are following some normal procedure of the data splitting. So we create different data boxes. One is training data, then we have validation data and test data. And the next point was that we have developed several models. So several models with different topologies, different hyperparameters, and all of these models were then fitted. You can see in this process the training data and the validation data were used. And then we result with one final model, one winner, so to say. And then this final model was provided with the test data and finally evaluated. Now I want to speak a bit more about the model creation. And one very important aspect here is the data. I have shortly touched on that. We had more than 6,000 different images. And one question that you have to ask yourself is the data that you're working with balanced? And you can see it's not perfectly balanced. We have one majority class with roughly 46% of all observations. So this is important to keep in mind if we in the end want to evaluate quantitatively the performance of the algorithm. We are making use of certain metrics like accuracy or others. And then this value that you get out of this process needs to be compared to the baseline classifier. And a very naive or baseline classifier would be to always just take the majority class and predict this one, and directly with this approach achieve 46% accuracy. So this is just what you have to keep in mind when I later speak about the accuracy of the final model. All right. I didn't speak about the time duration. So as I've said, the phenomena are mainly happening in the winter period. So we have simulated two different periods of 4 months each, starting in November and going all the way until February. So here you can see the final model that we have developed. So this is a convolutional neural network that we have created for this task. And we are having our input layer at the left-hand side with the images, with the dimension I spoke about earlier, and then follow some convolutional layers and max pooling layers. So there is a first convolutional layer, then a max pooling layer, and then this architecture is repeated again. Then we are having a flattening layer. And then at the very end, we are having 3 output neurons, which are corresponding to the probabilities of the 3 different classes that we are going to predict. All right, then there is one specific aspect that I also want to talk about. There is the question or the problem that we want to solve, or the question that we have to ask ourselves is the class of the image that is predicted, is that relevant to the location of the wind farm? Because that directly corresponds to the dimensions of the cross section that we are simulating. I've said we are having a height of 4 kilometers and a length of 100 kilometers. So the wind farm, even if it's a larger wind farm, is only represented in a very small fraction of this overall image. And then we are using a specific technique which is called class activation map. And this is an additional filter step that we are applying after we got the probabilities for the complete images. Then we can use this technique of extracting the class activation map to see which areas of the predicted images are most relevant for coming up with the class. So let's assume this is one example of a downslope windstorm. Then you can see with the red values, these are areas where we are having some high values of class activation. And then the blue ones are low values. And the idea that we are following up here is if there are only low values of class activations in the area of the wind farm, then we still don't create any alert, because then there might be some critical event in the complete area, but not that might not be relevant to the wind farm itself. Okay, now I want to speak about the model validation. And at first, I want to speak about the quantitative approach. So typically in classification problems, you're creating the confusion matrix based on the test data. And in the confusion matrix, you are presenting the true observations and the predictions of the model. And then the correct predictions are to be found on the diagonal line. So let's just stay on the top left. Here for this area, we have seen that there are 301 times images where the true label is 0, so normal behavior or normal wind, and 301 times the prediction was also the same. So that was a correct prediction, and the same holds for class 1 and class 2. But the interesting part here are actually the false predictions, and these are found to be outside the diagonal line. And overall, if you just take the complete number of all images that were analyzed, and if you take the diagonal line and divide it by the total number of observations, then you get the accuracy, which is 98%, and this is way above the 46% of the naive classifier. So that is what we consider to be a very good result. And the main takeaway, what also made us quite happy, is that the misclassification only happens between the class 1 and class 2. And class 1 corresponds to hydraulic jump, and class 2 corresponds to downslope windstorm. So there is actually no misclassification that is correlating between class 0 and any of these critical events. And that's the main kind of prediction that we want to have. And also the domain expert told me that it's sometimes for a human analyst not that simple to differentiate between these two different phenomena. So yeah, we are considering the model to be quite well. So we move forward and currently deploy this into production. Also, we performed some more qualitative validation. So we have here some sample output, where we can see for a certain previous period that we have resimulated, we can see the wind speed as a blue solid line. And then we can also see color-coded as orange the hydraulic jump and the downslope windstorm. And then the vertical y-axis, this one, the right one, is also corresponding to the probability of occurring of these different phenomena. So we can see there are specific times when the algorithm is quite sure that there is some of these two different events happening. And then we also can see here these black dashed line, and these are coming from our internal unavailability reports. And we have analyzed many of these images to see if the predictions of the model are corresponding to something that was actually observed in the past in these wind farms. So overall, we are quite confident that the model is working very well. And you can see the same wind farm and a slightly different period. And here you can see a longer period of the second type of critical event of the downslope windstorm. And also here we are seeing a very good example of what we are looking for, because in this time period we can also see the true observations of the wind speeds as a green solid line. And then as comparison, we have the blue solid line coming from the WRF output. And when we are having these critical events, then you can see that there is a strong underestimation of the wind speed during that time period. But still, the deep learning model is correctly predicting this phenomena. And also you can see that there is some incidence coming from the unavailability report. And yeah, the period is also matching with damages that were observed in two wind farms directly related to these high wind speeds. All right, with this, I reached the end and I will talk about some conclusions. So we have developed our extreme wind event forecasting system in the beginning for a very big wind farm cluster in Mexico. And this model is consisting of two different parts of a WRF simulation, and the outputs of the WRF simulation are then the inputs of the deep learning model, which is then outputting the alerts and the predictions of the critical events. The model performs very well, so it has a very high accuracy, and yeah, most of the large corrective incidents that we have seen over the last 2 years were correctly predicted by the model. And currently the deployment is ongoing of the model. So we are currently deploying it as part of the Siemens Gamesa operational weather forecasting system. And in the future, we plan to apply this in even more complex terrain locations, which might be affected by very similar extreme phenomena. And also the model can be used to study areas of interest where we don't have any turbines yet, but where we want to locate turbines possibly. Okay, so with this, I have reached the end of my presentation.